A new age in rocket-borne spectroscopy had just begun when Allen joined Culham Laboratory after moving from Aldermaston in 1962. Whilst at Aldermaston, aided by skilled engineers, Allen created his first spectroscopic treasure, the famous grazing instant spectrograph, on which so much depended. I had the good fortune to join Allen at Culham in 1962 with the spectroscopy division of the Zeta research team, which transferred from Harwell under the excellent leadership of Sir Robert Wilson. Bob's division initiated studies of spectra of highly ionized atoms from high-temperature laboratory plasmas. When the first rocket-borne spectrographs retrieved spectra in the solar far ultraviolet, spectra between 1960 and 62, most of the spectral lines could not be accounted for, in spite of previous research in line identification. During a visit to Culham Laboratory in 1963, Professor C.W. Allen pointed out that the strongest lines in our Zeta fusion plasma looked remarkably similar to unidentified solar XUV lines. He and Carol Jordan had compiled solar wavelengths from American rocket data. Our measurements for the strongest Zeta lines were identical. To tackle the outstanding line identification problem, Allen and I built a coaxial 100 kV low inductance spark by variation of the inserted material, the electron configuration, and applied voltage. Successful separation of lines from different ionization stages was achieved between potassium and iron. Derived energy levels were plotted down to and beyond calcium where existing line classifications were known, therefore establishing dominant ion line identifications. To provide further confirmation, Allen graphically illustrated 4-to-3 configuration interactions. The strong solar and Zeta lines were thereby identified as ion lines of ion 9 to 12. Further detailed classification of ion 9 to 16 firstly required time-resolved spectra facilitated by Allen's high-speed rotating shutter fitted to his spectrograph. Secondly, initiation and application of laser-produced plasmas. Thirdly, for the best spectra, a theta pinch which minimized injected purities, thanks to the special design contributions by Allen, based on specifications fathomed out by Kunze. Time-resolved spectra of the theta pinch, seeded with elements under investigation, resulted in excellent differentiating ionization stages. These not only advanced ion 9 analysis, but also spectra of many elements which remain treasures for those studying solar spectra. Julia Delzana and Helen Mason, for instance, have recently applied these theta pinch spectra in their iron project and related collision studies. These ion lines are therefore a major key in solar diagnostics. In 1966, Allen's team built, in weeks, not years, high-power ruby and neodymium lasers, which were focused onto targets to generate spectra. The Cullum group therefore initiated the field, spectroscopy of ionized atoms generated with laser-produced plasmas. Three properties which were to make laser-produced plasma spectra an invaluable tool in this field were immediately demonstrated. Firstly, they were almost free from impurity lines. Secondly, restricted ionizing stages were favored, which were spatially separated, enabling their discrimination. And thirdly, the high density led to the population of many high energy levels not occupied in low density plasmas. This gave the study of atomic spectra a whole new dimension. And during the 1960s, Allen's group reaped the harvest. Laser-produced plasmas consolidated the foundations on which energy levels were built by filling in the majority of gaps in the spectra of these ground configuration. At Lund University, Professor Ed Lane used our results in his famous ground term studies. At Lund also, Joe Ekberg and other colleagues added precise measurements in the ion isoelectronic sequence. The study of satellite spectra due to dielectronic recombination became one of Allen's long-standing interests. His publications on the subject led to a multiplicity of satellite-borne diagnostic solar flare experiments championed by major international projects. Allen shared with Carroll the identification of the helium-like singlet S to triplet S1 forbidden line in X-ray spectra. They then applied this forbidden line to estimate electron densities through the comparison of the intensity with nearby intercombination and resonance lines. During the 1970s, Allen's destiny went upwards in more ways than one. His interests rose to the sun and stars, and he took up full responsibility for scientific leadership. Allen was co-author of a paper reporting the 1970 solar eclipse observations. This unique experiment retrieved vacuum ultraviolet stigmatic spectra recorded with a slitless Wadsworth rocket-borne spectrograph. It displayed loops, flares, forbidden lines, and was therefore the prelude to recent spectacular solar observations. Using these eclipse spectra, Allen pioneered measurements of the Lyman alpha corona. Bob Wilson's division, meanwhile, became the astrophysics research group under the Science Research Council. Later, its leadership passed to Allen. His ARU eventually joined the Appleton team, and both were moved to form part of the Rutherford Appleton Laboratory. Allen adopted the same style of leadership, adding his own experience and innate talent. Firstly, he injected physics into engineering projects, no doubt founded on his first-class knowledge of both theoretical and experimental physics. Secondly, he was a talent spotter. He demonstrated the intuitive gift to find the reliable authority when seeking advice, and the capable scientist and engineer to join his team. Thirdly, he would steer well-conceived proposals through committees with persistent persuasion, always finding the extra time we needed. It is not surprising that the complex payloads, such as Chase and SMM, were successfully prepared for space during his reign as a division head. Alan's previous interests in the Lyman Alpha continuum, X-ray spectra, and instrumentation meant that he possessed the necessary experience to participate in the design, planning, preparation, and analysis for the Chase experiment. Alan was a principal investigator for SMM, complex X-ray polygrammator. He was involved in all SMM stages from proposal to launch. Therefore, the project benefits from his expertise. On his watch at RAL, his team dealt with a flat crystal instrument structure and assembly, crystal drive, raster mechanism, and electronics. He chose his team wisely and successfully supervised this complex payload. Analysis of the FCS spectra was facilitated by the theta pinch source and laser-produced spectra. International teams joined with complementary research, both from space and the ground, notably at NRL by George Doschek and Yuri Feldman, and by the Lebedev Institute. Hitherto unknown flare and other spectra were therefore made available. Project partners, MSL and Lockheed, prepared bent crystal instruments, which produced satellite line spectra. Alan joined in diagnostics from these satellite spectra, which contributed to our knowledge of solar flares. With his leadership for the FCF payload, Alan lit the torch, setting the standard at the Rutherford Appleton Laboratory. Last year, Alan had the pleasure of revisiting RAL to celebrate their 200th satellite launch for payload, following the tradition he started. Now Richard Harrison carries the Flamers division. Alan clearly derives much pleasure from dedicated interest in physics. In addition, he enjoys a deep cultural appreciation. He has, for instance, a rich knowledge of music and likes singing in choirs. Alan's inspirational leadership provided the beating heart of a fertile triangle where spectroscopy of highly ionized ions germinated. Amazingly, this summary only covers the start of Alan's career, which culminated in France. France acquired one of England's best scientists. But Alan is an international player with a warm hand of friendship extended to all. The aforementioned treasures from his early years, including the spectrograph, the ion key to the sun, laser plasmas, dielectronic satellites, the solar eclipse studies, are just a few selected highlights. To this, Alan added a prolific theoretical solar plasma studies, and crowned all with his contributions to CHASE and SMN. Numerous speakers today have added a treasure trove of accounts of Alan's prolific contributions to science. Together, we have conveyed our appreciation of a colleague and a friend. Let us therefore wish Alan a happy birthday and thank him for the many treasures he has added to our knowledge and for his valuable leadership. Before I sit down, I just would like to thank the organisation committee and Alan for the pleasure of being here today. And I'll let you into another little secret. In 1952, I married the most beautiful girl in France. And I love France.
Thank you, Brian. Thank you, Brian, for this very complete